today we are going to talk about the experiment number 4, which is cyclic voltammetry. So what is cyclic voltammetry? So cyclic voltammetry is a basic electrochemical technique which is used to study redox behavior of a chemical species. In this, we apply a fixed potential window, for example 0 to 1 volt, in which we linearly sweep potential at a fixed standard in millivolt per second. In this experiment, we are going to use a redox couple, ferric ferrous redox couple. This is the electrochemical setup for the experiment, which is a 3 electrode system, in which working electrode is a platinum wire, reference electrode is a saturated calomel electrode, and the counter electrode is a platinum mesh. And the electrolyte that you are going to use is a K3FeCN6 electrolyte, which is a salt for this redox couple. This is the cyclic voltammogram which you will get after the completion of the experiment. So in this cyclic voltammogram plot, the y-axis is current and the x-axis is the potential. So in this cyclic voltammogram, it is divided into two regions. One is anodic region where the oxidation takes place, and another one is the cathodic region where the reduction takes place. So now we will see how the experiment or whatever happens at the interface, it's correlated with this plot. So when you apply a fixed potential window, that is in this experiment you are going to apply -1 volt to the +1 volt. So when you apply a potential window at a particular standard, for example, we'll take 100 millivolt per second as a standard. So when you start the potential from A, you can see there is a linear region. This linear region is particularly due to the only double layer capacitors or charged double layer capacitors. So when you go toward the higher potential, you can see that the current is increasing. It is because when you apply a potential to the working electrode, the Fe2 plus ions present in the solution convert into the Fe3 plus electron, that is oxidation takes place. So as you go toward the higher potential, the current is continuously increasing because of the oxidation process. So when you reach to the point B, the Fe2 plus and the Fe3 plus ions concentration is equal. So that means you reach at the equilibrium point. So when you move toward go toward higher potential from B to C, the most of the Fe2 plus ions present at the electrode surface converted into the Fe3 plus. So if you go toward more higher potential, you can see the current is decreasing because most of the ions present at the interface are converted into Fe3 plus ions. So the Fe2 plus ions which are present in the bulk is moving toward the electrode surface, because of which you are seeing the decrease in the current. Now when you reach to point D, we sweep potential back towards the -1. Here also you can see that initially the region is linear, which is because of the double layer. Then as you go toward the more negative potential, the Fe3 plus is converting into the Fe2 plus, and at point E, the concentration of Fe3 plus and Fe2 plus are equal. As you go toward more negative potential, the Fe3 plus, now most of the Fe3 plus which is at the interface is reduced to the Fe2 plus. So now again the Fe3 plus which is present in the bulk is coming towards the electrode surface, and because of which the current is again decreasing. You are getting this plot because of the Nernst equation, as Nernst equation correlates the potential with the concentration of the ions. So now what is the objective of the experiment? The first objective is to calculate the double layer capacities. So what is the double layer capacities? The double layer capacity is when you insert any metal into the electrolyte, the metal itself has some charge on it. So to neutralize that charge, the opposite ions comes from the electrolyte and adsorb on the metal surface, so which gives you the double layer. And when there is no redox couple present in the solution, only the salt is present, like a neutral salt like KCl or NaCl, you will get the plot like this, where you don't see any peak because there is no redox reaction happening. This is purely due to the storage of the ions. Then how will you measure the double layer capacitance? For that you need to integrate the area, and this is the equation for the measurement. So integration of IVTV, which is the integrated area that you will get from the plot. Then mu is the scan rate and delta is the potential difference between the initial and final potential. So second is objective is to calculate the formal potential. So to calculate the peak potential, you will need the cyclic voltammogram. In cyclic voltammogram, you can see at point C is the peak potential for the anodic region. So you have to take this potential as a peak potential for anodic region, and for cathodic region at point F, and take the average of this. So you will get the formal potential. Third is the calculation of the diffusion coefficient. To measure the diffusion, to calculate the diffusion coefficient, you will need the Randall-Seelig equation, which correlates the scan rate with the peak current. So in this, you have to first find out the peak current, which you have to use the cyclic voltammetry plot for that. So for measurement of the peak current, you have to extrapolate the line from this linear region. This linear region is purely due to the capacitive behavior, and above this this area is due to the redox reaction. So you have to extrapolate this line and take a perpendicular to the point C. So you will find the peak current for anodic region, and then there is N, which is the number of electron. So in this, only one electron transfer is happening. So N is your 1. A is the area of the electrode, which you have to measure. D is the diffusion coefficient that you have to calculate. C0 is the concentration of the analyte, that is Fe2 plus or Fe2 plus, and mu is the scan rate.
The electrochemical cell consists of working electrode is the platinum wire, counter electrode is the platinum mesh, and the reference electrode is saturated calcium electrode, and the electrolyte is 1 molar potassium ferricyanide in water. Okay. To measure the CV, open this EC Prayog software. Wait till the program loads in. Press OK. Connect the potentiometer to the computer. Go to experiment, select cyclic voltammetry. The initial voltage will be 0. The upper limit is 1 volt, 1000 millivolts. Lower limit is negative 1 volt. Final voltage is 0. Step size is 1 millivolt. Scan rate is 100 millivolts per second. Current range is 20 milliamperes. Initial delay can be 2, because initial delay is for calculating the OCP. So we don't need to calculate OCP since all the voltage is against the reference electrode. Equilibrium time can also be 2 seconds. Number of cycle is 3. Select the path, go to desktop. There is a folder MM224. In that experiment number 4, you can save the program with any of your group's roll number. Once you click OK, the experiment will begin. The initial voltage is 0 volt. So the first cycle is to be ignored, because you will take the first cycle to settle down the system and get to its equilibrium. The second and the third cycle should overlap with each other. The third cycle overlaps with the second cycle, and this is how the typical CV curve for potassium ferricyanide should look like.